If we start off with a solution of acetic acid, because you all remember, of course, that acetic acid will dissociate, not very well, but it will dissociate into the acetate anion and a proton. And I told you that the pKa for this was what? I can't hear you. 4.76. Okay. So, if we take a solution of pure acetic acid, you would agree with me if I had acetic acid and the most common, how many people here like acetic acid? How many people like to put it on your food? That's vinegar, right? So if you take a solution of acetic acid, and you would agree with me, right, that at the beginning, most of it is in the protonated undissociated form. That's the blue curve, right? And that there's not a whole lot of the acetate anion because it's a weak acid. It doesn't dissociate a whole lot. But if I now begin to add in equivalence of base, and what do I mean by the term equivalence? I mean one equivalent is the amount of base that equals the total amount of acetic acid I had in solution. Okay? And as I begin to titrate in these equivalents of base, what's going to happen, as you know, is that the OH minus anion that I titrate in is going to bind to that proton to form water. And because this is such a strong reaction, as I titrate in more base and consume more protons, according to Le Chatelier, I'm going to take this acetic acid and force it to become acetate anion. And so as I titrate in more base, the amount of acetate anion goes up and the amount of acetic acid that's undissociated goes down. And we can simply measure the pH at each point in time. So we measure the pH. I'm going to cheat here and put the answer that I want over here. And if we do this, what you find is a curve that looks like this. So it's basically a curve with a shape like this. I'll draw my points to match my curve. And this is what I measure. This is called a titration curve. Now, what do you notice about the curve? Anybody notice anything interesting about this titration curve? Well, look what's happening around here. The curve here is pretty flat. It's not till I get over here or up here that the curve starts to really change, and you can see that in the handout, right, which you have, and in this overhead that I'm showing you. Look how flat it is, okay? And notice that it has an inflection point. And where is that inflection point? The inflection point is at exactly the pH, right, where the acetate anion and the undissociated acid are equal. Okay? And you know that corresponds to the pH where the base and the acid are equal. So the logarithm term is equal to what? I can't hear you. 0. So the pH where the inflection point is, this is the pKa. And that's how I determine the pKa experimentally. I don't have to do it just for acetic acid. You have a handout that shows the other curves I can do this with. Guess I'll draw one more on there. I can do it, for example, with ammonia, NH3+. And if I do, let's use a different color. If I do this with ammonia, what I get is a curve that looks like this. Okay, so that green curve there corresponds to the reaction. NH3+ dissociates into NH2 plus a proton. And again, same deal. As I titrate in the base and suck up the proton, I dissociate the ammonium into ammonia. And I look where the inflection point is for ammonia. And that inflection point for ammonia turns out to be the pKa, which is 9.25. And I can do this for imidazole, I can do it for phosphate, I can do it for anything I want. Okay? Nothing tricky there. I'm going to do the exact same thing, but I'm going to do it this time for phosphoric acid. H3PO4. And if I plot the pH, 14, 12, 10, 8, 6, 4, 2, 0. You'll notice that phosphoric acid has 3 protons, right? Now that means that I'm going to have to add 3 equivalents of base for every molecule of phosphate to titrate these 3 different protons. And when I do that, what I find is a curve that looks like this. I get a curve that looks like this. Clearly, it looks like there are 3 points. Sorry, I drew this wrong. Let me draw it a little bit better. That's a little better. There are 3 separate inflection points that I get on this curve. pKa1, pKa2, and pKa3. This means that this is an example of a polyprotic acid. And for phosphate, pKa1 is about 2.15, pKa2 is about 7.2, and pKa3 is about 12.4. Okay? And really what's happening is the following. I have H3PO4, which has its first pKa when I get H2PO4 plus a proton, single negative charge. And this pKa is about 2.15. And then I have a second reaction, which gives rise to a proton, and HPO4 minus 2. And this has a pKa of about 7.2. And then I have a third reaction in which I dissociate another proton, and now I have the phosphate ion alone with a charge of minus 3. And this pKa here is about 12.4. Now, is there a reason, is there something special about that pKa of 7.2? What's the normal pH of your body, of your blood? 7.4. So because that pKa is pretty close to the pH of your blood, phosphate makes a pretty good buffer. To understand that, we're going to have to talk a little bit about what we mean by a buffer. Okay.